Here's a look at quiz 1 in a step-by-step fashion. The overall goal of this particular quiz is to figure out whether or not a centrifugal pump can be placed above or below a large reservoir. So let's try to break this down. The flow rate is about 0.8 feet cubed per second. The net positive suction head has been defined as 18 feet, and that's again the required. The water temperature and pressure are given from the reservoir. We assume that the dominant pressure drop on the suction end is a debris filter to make sure the pump is not destroyed by any debris in the reservoir, and that could be placed in this location. The pipe suction diameter is fixed, so that size of diameter is known, and then the vapor pressure and specific weight are 0.33 psia and 62.3 pound-force per foot cube respectively. So what we're going to do is look for the maximum length, Z max, below or above the pump so that cavitation is avoided. If the maximum length is not possible, we're asked to explain our options. So let's attack it. First, what I want you to do is think visually about this pump, and think also that most pumps require some elevation head of a reservoir above a pump. So this is sort of an awkward configuration right now, just from a practical perspective. So let's think it through. We're going to look at the givens and be very clear about what we're seeking to find. So I'll rewrite the givens: flow rate, NPSHR, the temperatures. I did actually give you the specific gravity, or specific weight I should say. I've identified the inner diameter of the tube and the loss coefficient. I then want to be clear about what I'm seeking to find, so I make sure it's Z max, and we want that elevation changed to ensure that there's no cavitation. The best place to start this problem is to identify points, and we've been given a nice hint about points 1 and 2, so we identify those, and we want to be clear about the control volume, so we might label it so there's no confusion. Notice that this control volume does not include the pump. Writing out on the left-hand side, P1, V1, Z1. On the right, P2, V2, Z2, and the loss. Again, there's no pump nor turbine, so the only H that comes in addition to pressure, dynamic, and elevation heads, is the loss. What we need to do next is decide what comes and what goes, or what stays and goes. P1 stays because when we're dealing with a problem like this, we always deal in absolute pressures. The velocity of a large reservoir is always 0. The elevation at point 1 is considered 0 because it's a datum. It's a point in which everything else is referenced. P2, we keep it. Again, we're dealing with absolute pressures. Keep in mind, as flow goes from 1 to 2, P2 will be less than P1. It has to suck it up. Think about a straw. When you're having a nice thick shake, you've got to create that vacuum at your mouth. So that's what a pump is doing. Z2 is the height. And finally, the loss. The loss is dominant due to the debris filter here. So now we reduce it, and we solve and group things based on our knowledge of net positive suction head. So we've grouped P1, we've grouped it with Z2 and HL. The remaining items on the right-hand side are P2 over gamma plus V2 squared, 2G. This is called the suction head, and it's really the stagnation head at the inlet to a pump. This value minus the PV over gamma, P sub B, again, is the vapor pressure. That does equal your net positive suction head. Okay. As you go further, you'll find that we can now group these as a net positive suction head available and the net positive suction head required. In this case, we always want the net positive suction head to be greater than the net positive suction head required. So we set up this inequality, and we assume that quality means that that's when Z equals Z max. Now, because we've been given the net positive suction head required, we can substitute a numeric value for NPSHR and simplify so that we can solve for Z2. So we'll get that back. Okay, now it's back. The substitution of all the givens take place next, and we're just methodic about it. It's a plug and chug situation. We solve for Z2. Each unit is in feet. We come up with a negative value. What would a negative value mean? If it's not positive, it means that the location of this pump, instead of being above the reservoir, is below the reservoir. So the actual location of this pump is below this reservoir. So the answer would be, can it be, the answer to whether or not it can be above is no, and it has to be at least 20.46 feet below the inlet, or I should say the top of the free surface of the reservoir, to avoid cavitation. What could we do to ensure that cavitation would not occur if that distance was not available? We've got a number of options. We can certainly change the pump, change delta pump, shorthand. We could increase P1. We could decrease the head loss, and we could decrease the temperature. If we thought that the max height was a positive value, but we had a lot of depth, we could certainly reduce that distance or increase the distance of the pump below the reservoir. But again, I think the primary ideas to improve the cavitation situation here would be to change out the pump, increase the pressure, certainly reduce the head loss, or decrease the temperature. I hope this has been helpful. I think the critical elements when you look back are to identify the energy equations properly, to recognize that you can group them basically into easy terms, in terms of P1, Z2, and HL. Those are easy to obtain. P2 and V2 are more difficult, but because they require you to bore into the pump and get very close to that suction head. And then once you can group them, it's a relatively straightforward exercise of equating NPSHA to NPSHR and solving for Z2. I hope this was helpful. Thank you.